Hi everyone, welcome to the virtual star party. This is Scott Lewis. I am here on December 23rd of 2012. The world did not end, and woot. So we're going to do what we're normally doing. We planned this anyways, so let's go. We're going to go ahead and view actually the Sun, Mercury, and Venus this evening, or today with Paul Stewart in New Zealand, since all of our North American astronomers are clouded out. But with me today is the amazing, as ever, Thad. You want to go ahead and introduce yourself real quick while I share this all out?
So, yeah, hi, I'm Thad Szabo. I'm an associate professor of physics and astronomy at Cerritos College in the Los Angeles area. And, yeah, I guess I'm kind of strange as far as these, well, anyway, but yeah, as far as astronomy people go, because I've done research in it, but I will also get out my own telescope and look. I mean, there's a lot of people in the field who you give them data and they know how to churn through it pretty well, and there's a lot of amateurs, not putting down amateurs make terrific contributions to astronomy who can give you a great tour of the night sky, and maybe have even contributed to research. But I tend to like to do both. I mean, kind of really live and breathe this stuff. So yeah, so hopefully I'll be able to share some of what I was able to get from about a year ago. I was in Death Valley and Lone Pine in the eastern Sierra Nevada mountains in California here, and it was cold, but I'm hoping that what I show you shows it was worth it. So.
Absolutely. We'll break the rules tonight.
All right.
Or
Breaking
today.
The rules.
Breaking the rules. You know, Fraser's away. I'm taking over the world. Sorry about it. And our astronomer today is the amazing Paul Stewart, who seems to always come through for us whenever, well, anything's happening, whether good or bad. Paul is always there. So you are awesome, Paul. And what are we looking at?
This is Venus during the middle of the day. Well, middle of the afternoon, I should say.
So what time is it there?
It is 3 p.m. on the 24th.
3 p.m. on the 20th, from the future. This is amazing. So the world ended and now we have the future. No, we've always had the future. But so we're looking at the planet Venus in the daytime sky. Now, most people can't really think about this, but that we are able to see many different objects in the daytime. Dad, can you go into why we're able to see these things when it seems counterintuitive for it? I
mean, yeah, most people probably have some experience saying, hey, why is the moon out during the day? In fact, I think there was even an episode of 30 Rock where they had Buzz Aldrin yelling at the moon during the day, why are you out now? But that's the thing. It's that the sky itself, because it's scattering all of this light from the sun, can show up very brightly, bright enough to make it impossible to see most objects against the brightness of the sky. But the moon, being large enough, reflecting enough light, does show up against the blue sky. And if you know exactly where to look, Venus is actually quite visible during the daylight if you know exactly where to look. A pair of binoculars would bring it out pretty brilliantly. And obviously with a telescope you can look here, and you can even see around Venus here there's definitely that blue tint. Yeah, that is our atmosphere scattering light from the sun. And you're like, okay, well can't you get the darn planet to sit still? I mean it keeps going fuzzy and all this. That's one of the issues of trying to observe during the day. You have all of this heat being dumped into the atmosphere from the sun. And sometimes things will settle down pretty well, and you can see Venus is very nearly round. But most of the time, it's a little bit like looking over a barbecue grill. And so with that, if you've been out at a picnic or something, and you've tried looking at somebody over the heat from the coals, that everything gets all kind of wavy behind it. Our atmosphere does this on small scales all the time. And so when you look with high magnifications like this with the telescope, all of that waviness gets magnified. In astronomy, we call that bad seeing. So during the day, it's more difficult to get good seeing than it is at nighttime, just because you get all of this energy input from the sun, causing the atmosphere to heat up and swim around like this. But still, this is actually, considering when I've tried imaging Venus during the day, this is actually really good. So
yeah, it's amazing. You can actually see that it's not quite full. So we think about the moon being full. You see the perfect sphere. And we have gibbous, which means humpback, so it's kind of oblongish. And you can see that Venus right now is in a gibbous state, which is awesome. So you can actually see part of that.
So, I mean, you know, what's going on here is, I mean, let's say that this is the face of some object in space. And so if it's crescent, this isn't a very good example because this is a disk instead of a sphere. But crescent means, I mean, you can see a little bit of like one edge of something, right? So gibbous is kind of the opposite, where you can see all, but a missing crescent, right? And so that's kind of the phase that we have here with Venus right now. It's on the opposite side of the sun from the Earth, heading toward what's called superior conjunction, when it lines up with the sun in the sky, but it's on the opposite side of its orbit from where Earth is. So inferior conjunction happened this past June 5th, when Venus actually moved directly between the Earth and the sun. So the distance from Earth to Venus was inferior to the distance from the Earth to the Sun. Coming around, I guess it's going to be this spring, Venus will look like it passes behind the Sun from our perspective. So now the distance to Venus is superior to the distance from the Earth to the Sun. So it's called superior conjunction.
Right. So it's just based on where it is in its orbit, where we are in our orbit, and what's going on there. Because it's all relative. What we're seeing is because we're two moving bodies around the same star. And so everything is going to be relative. We're both moving. We have to adjust for that, and we get to see different things as that's happening.
Absolutely. And I mean, a good way to go play with this, I mean, one, we were talking about Celestia last week when we were having the VSP with Nicole. And let's see, Teal, I guess, was trying to bring us some stuff from
Australia. Our amazing Southern Hemisphere astronomers have been pulling their weight, when the North American ones haven't. Come on, guys.
So
clear up your skies.
But so Celestia is one way to play with this. Another one that's also out there, it's just a website. It's called skyviewcafe.com. And there's a tab at the top. If you load it, you wait for Java to load the applet. At the top, there's a tab that says Orbits. And so if you click on that, it shows you the positions of objects in the solar system. And so you can run time forwards or backwards or set a specific date. You can view the solar system, all the way out past Pluto, or as close as from the Sun to Mars. And you can see where the planets are relative to each other. So one thing that you could potentially do is say, okay, hey, show me the time, show me the orbits now, see where Venus is relative to the Earth, and then let time go ahead. And you can see that, because Venus is on an orbit closer to the Sun than Earth, it's going to go faster. And so what you'll see is Venus getting a little more ahead of the Earth, a little more ahead, and so come next spring, it'll be opposite the Sun from where the Earth is.
And it's something to think about too, that because it's closer, it does move around faster. And I think the best analogy I've come up with, as far as people have their day-to-day understanding, is a tetherball. So the further out a tetherball is, it's going to go around longer. But the closer it is, it's whipping around really fast. Because it's got the same mass and everything like that. And so that's the way that I tell my students, hey, just think about it this way. I know, well, maybe I'm kind of old now. I don't know if they have tetherballs anymore.
Yeah, I mean, it's the thing. You have this issue. Oh, a kid might get hit in the face with the ball. Well, that's the fun of it. No.
Yeah, no, it is.
So, yeah, I mean, there's a lot of things to be great. Like, okay, so as part of our class today, we're going to go out on the playground, and we're going to try this. So, yeah, I guess at this point it might be, well, we'll show you a video of video footage of tetherball from 50 years ago or something. But yeah, instead of let's go out and see who can get it past the other person, right? So, but yeah.
And just a quick reminder, everyone, I am tracking all the comments going on here through the event pages. I've set up actually a couple through the communities as well to test that out, so I'm not sure since communities are new. But we do have our event page on the Virtual Star Party page that share through my stream, and any reshares from there, I'll be able to check comments. Also on Twitter, if you're watching on CosmoQuest or any other embedded places, I'll be able to check your comments via the hashtag StarParty. And YouTube, I am able to check all the YouTube questions as well. So feel free to leave us comments, suggestions, questions, bags of money. Please leave bags of money. if you can. But so yeah, if you guys have any questions or comments, I'm seeing a couple of them roll in right now, so I thought I'd just make sure everyone knew that you could do that as we're going on through our broadcast this evening. And
they like this. There's probably a Tetherball app.
There absolutely should be.
I guess if you hold up your phone and swat it, and maybe somebody else is linked in and they're swatting their phone somewhere else.
That's right. That's awesome. Now, I have a question here from Tom, which is not regarding the science, but regarding Pamela and Fraser and their Mesoamerican expedition. I haven't heard from them directly, besides some via emails, work-related, but I think they're back in the States now. And I've seen tweets go out, which probably means they are, but not back home yet. So we look forward to having them back home safe. And enjoy their time when it was really cold here in Southern California, and they're over there in the Bahamas.
Yeah, it's been strange. I mean, I was out. I did have the scope out. My brother lives in Venice now, and he has a place that actually has a backyard. So, so we were hanging out with the scope and got to show a couple of people the moon. I mean, the moon just looked amazing on Friday night. The Clavius crater was on the border between the unlit and the lit portion of the moon, called the Terminator. Not that kind of Terminator.
Yes, it is that Terminator.
Oh no, in the coming Skynet. All right, so
it's not a crater.
It's not the crater. So, but the thing is, you could see the rim of it lit up, and then inside of it you could see some other craters. So there's the Clavius crater and the craterlets. And so it's a band, right?
That sounds like it sounds like a Motown group. That's awesome.
So, and we're hanging on the Terminator. No, so, but oh gosh, no, I have soul. Never mind. All right, we'll have to do this at AAS. But yeah, it looked really good. We had we had Jupiter, and the 4 Galilean moons were present. I was able to get some photos of that. Let's see. And one of the guys there, he had recently written a poetry collection, and for the cover he used a picture of the Orion Nebula. I'm like, hey, you want to see the cover of your book? And so, brought that up in the scope. And yeah, so, we were all kind of hanging out and checking this stuff out. So.
And that is, the Orion Nebula is one of those that it to me is on par with Saturn. Being able to see it. I mean, everyone knows Saturn, is able to recognize it because they've heard of it, they've seen it in books, but you can faintly see that there's something there in the man in the sky. Everyone knows the belt, or at least most people know the belt, and they see something down there. But when you're able to resolve that detail,
the dagger, right? It's a dagger.
The dagger, yes, that's what it is.
That's what it is.
That's actually a subject of my other show, but that's not safe for work, so we will not be talking on that end.
But yeah, I mean, you get this hint of fuzziness, and then bringing it in with the scope. I mean, this very green glow, and it's only green because that's what our eyes are most sensitive to. Really, if you were going to take a photo of it, red would be the predominant color because of all the hydrogen present, but our eyes are way more sensitive to green than they are to red or blue. So if when you look, it's light, your eyes are like, hey, the rod, it's only rods here, no cones. But if the cones are going to turn on, they're going to turn on with the most, whatever they're most sensitive to. So it ends up, this kind of ethereal green glow around those very 4 bright stars in the center. It's like, hey, those are baby stars. Okay,
they are. It's a stellar nursery. It's insane. Yeah. To think about that. We see our star, the sun, and sometimes it's even difficult to understand that our sun is a star, because we look out and we think stars, we think little pretty dots in the sky. But then to realize we can look at a place that literally brand new stars are being formed. Right now what we're looking at is new stars being formed. It's something that's really difficult to comprehend, that they're still being created. There's still a process happening where they're coming together, they're forming a main sequence maybe, or exploding, and stuff happens.
Right. I mean, the time scale here is also kind of difficult to get across, because we're used to, all right, okay, so you had a kid last year, now the kid's a toddler, okay, 5 years later, they're starting school, whatever. Here, it's going to take tens of thousands of years for that gas to even collapse to get to the point where it will start heating up. It's going to take another tens of thousands of years, hundreds of thousands of years before the pressure gets high enough inside to start fusion. All right, and now, okay, now you have a star. Your baby star has actually been in the process of forming for a couple 100,000 years.
Right.
So your baby star, it's already, you know, close to 1 million years old. And your bigger ones, they're not going to last that much longer than that, and that's again the case with these at the center of the Orion Nebula.
Right.
But yeah, the whole idea of anywhere you look in space, compared to the time that it takes for most of these things to evolve, you're really getting something that's very kind of frozen in time compared to the length over which you're seeing anything happening. You know, it's a little possibly depressing to some people to tell them, hey, Saturn's rings, those aren't permanent. Right. On the other hand, hopefully people can see kind of glass half full that, okay, we're around at the right time to see them. If we'd been here, you know, several tens of millions of years ago and invented the telescope and got a look, Saturn would just be another interesting, large gas giant, but not with this spectacular ring system. Tens of millions of years from now, somebody looking at Saturn would go, okay, there's another gas giant. What was the big deal with this thing? So I mean, yeah, we're kind of here at the right time at whatever moon got destroyed.
It's got ears.
It's got ears, yeah. Yeah. Of course, later on, with Triton being in orbit around Neptune the opposite way that Neptune spins. And this is a problem for any object in space. If you have the way that the Earth spins, the moon goes around the Earth in the same direction. Right. And so with this, it actually ends up slowing down Earth's rotation. And to compensate for this, the moon gets a little bit farther away. I mean, it's a very, very tiny amount that its orbit stretches. Right. You have the opposite problem if something orbits in the opposite direction from which a planet spins, or if it's orbiting faster than the planet spins and in the same direction. So for one example of that, you have Phobos, one of the moons of Mars, orbits Mars so close and so fast that if you were on Mars and watching it, it would rise in the west and set in the east. Because it's just whipping around Mars that quickly. Or something like the largest moon of Neptune, which is Triton, is in what's called a retrograde orbit. So if you think of retro, like big gold chains, and nobody wants to see chest hair and all this, but you know, if we go back to the 70s, oh geez, this is my brother posted a Christmas picture of myself and my two brothers with Santa from 1978, and what I was wearing. Oh,
we'll
boy.
have to go into the event photos. Now that you've mentioned it, you need to post that.
I'll have to go dig that up. So that's retro, right? Thinking of going back to something in time. In scientific terminology, retro means backwards, right? So backwards from usual motion. And the usual thing is if an object is spinning one way, things orbiting it are also going around in the same direction. Triton, the largest moon of Neptune, orbits retrograde compared to how Neptune rotates. So it's going to have the opposite effect that our moon has. Our moon is getting farther away and is slowing down our rotation. Triton's going to get closer and closer, and eventually it will cross close enough to Neptune that Neptune will tear it to shreds. And Neptune will have the kind of ring system that we see around Saturn now. So, so instead of, you know, fairly nearby, 10 times the distance from the Sun gas giant that we have with Saturn, you'd have the one that's 30 times the distance from the Sun, but this this deep blue-green ball with what will be this incredible ring system around it. Now, this isn't going to happen in any of our lifetimes. But,
unfortunately,
but if you're watching this, you know, a couple tens of millions, hundreds of millions of years from now, you know, we're already mentioning you're getting this really cool Neptune system to look at then. So.
Right. So, as we're going along, Paul is, we're looking at Venus right now, so, we're looking at a planet in our solar system, and Paul's actually going to move to another planet before we finally rest on the Sun. Where are you going to head us to, Paul?
We should be going off to Mercury.
Off to Mercury!
Can we see Messenger?
That would be awesome. I don't think we can, though. No. Messenger is tiny.
Oh, really, really, really tiny. Is Messenger in Celestia?
I'm not sure.
Okay.
And I only have the one machine up right now, or I would check on the fly.
Yeah.
But that's one thing. That's one of the software I use for our virtual star parties is Celestia, which is a 3-dimensional I guess, a way of touring the solar system, and they do have the orbits of different spacecraft that we have. So you can see the International Space Station. You can see, I believe you can see the Lunar Reconnaissance Orbiter. I know you can see Cassini. And I can see Mercury. That is awesome.
Okay, so we just got from the comments, Messenger is not in Celestia.
No.
Thank you, Jake Demare.
Jake, you're awesome.
All right. Now the thing is with Mercury, first of all, it's tiny. I mean, compared to Venus is roughly the size of the Earth, so that's a much larger surface for sunlight to strike and reflect back at us. You know, Mercury is between the size of our moon and the size of Mars. I think if you were to compare Mercury to, really from the diameter of Mercury is comparable to the size of the United States from like Maine to San Diego.
Oh, wow.
Right?
Yeah.
So, I mean, if you were going to hold Mercury like in front of the Earth and get some feel for comparison, the Moon is smaller than that. The Moon would kind of cover the western U.S. Mercury would pretty much take up, you know, the U.S. from side to side, as opposed to Venus, which is roughly the same size as the Earth. So it's not as big a target for sunlight to bounce off of. With how much closer it is to the Sun than Venus, it's never, you know, it's never very close to us. The closest it can get to us is about on the order of like 55 million miles away or so, 50 million to 55 million miles away. And the other thing is just the material it's made of. Venus has this very bright atmosphere. The atmosphere of Venus actually reflects something like 3/4 of all the light that hits it. Whereas Mercury, it's, you know, I'm trying to see if I have something. I guess if I have this black Sharpie and I were to draw on some paper or something here, right? That black mark, I mean, that's not much less reflective than Mercury.
Right.
Mercury's, the amount of light that Mercury reflects of all that hits it is something like 7 or 8%. So it is not a very good reflector of the light that does strike it. So the fact that we're able to dig it out from the background of the sky here is pretty amazing. Yeah, nice job here, Paul. Especially with the seeing. I mean, the seeing does keep blurring it almost completely out of the view, and every once in a while we get this nice calming of the Earth's atmosphere, and we do get a view of it. So yeah, really good job here.
And it's pretty warm down there right now, right? You said it's around 30 right now, Paul?
30 Celsius for
30
American
Celsius,
audiences.
yes. Sorry, Americans. 30 Celsius.
It's 30 in the dome anyway. It's colder outside.
Colder.
Yeah, it's only
because
20.
it's summer. It's now summer in New Zealand. So while we're complaining about it being cold, you've been complaining the entire time we've been having our summer. So, and you've still gone out and observed for us because you're awesome like that. Now, what telescope and camera are you using right now?
Right, we're currently using a 12-inch Meade with a little imaging source camera on the end.
Okay. So 12-inch, we're talking about the diameter of the mirror, the primary mirror there, right?
Yep.
And what type of camera you said you're using?
It's an imaging source camera.
Okay.
Can't tell you what the number is.
That's one of the DMKs, or?
Yeah, it's the color one. I think it's DFK.
Very nice.
So, I mean, essentially, this is it's essentially like a webcam, but again, you know, they make them with higher frame rates and better control over the gain and sensitivity for doing imaging of planets and the moon. It's especially nice to be able to capture lots and lots of frames a second, so that way all this kind of swimminess that you're seeing caused by the Earth's atmosphere, you can average that out. Right. So so these kind of cameras are ideal for this kind of purpose.
And then we get to share it with you because, again, Paul is... I swear, Paul, as long as I've been working with you now here at the Virtual Star Parties, I think you've only had weather take you out once when we're planning on it. So I don't know if you're just not buying equipment ever, and so you get clear skies, because that's one of the superstitions that goes on. Someone buys equipment and you have clouds forever. So I think there's a lot of telescope purchases right now in Christmas in the United States, and so that's what I'm hoping. And so we're all cluttered out. But no, it's that the 12-inch meet. I've got a 12-inch meet on campus that we have set up in our lab, and it's really great. It's a lot of fun to use.
So I see we've gone to, is this a lower magnification that you have in there now, Paul?
Yes, it is.
Okay. And so that keeps the light a little bit to a tighter group of pixels on the camera. So instead of kind of spreading it out, it keeps a little bit tighter, and so we can keep it in view a little bit better since the light isn't being spread out quite so much. Okay. Nice adjustment. Good. Yeah. Good adjustment to make.
Yeah, that's great. And I mean, we're looking in the daytime in New Zealand, and we're still able to resolve planets because it's just bright enough to be able to go through the scattering of light that we're seeing in our blue sky. And do you know how far away Mercury is right now?
Not sure. Let me see. Oh, wait. My other machine's running Linux, and I don't have the Java plugin.
Oh, okay.
So I do have, hang on, I can bring up Stellarium. Let me do that.
Yeah.
That's right, because Stellarium, you click on an object and it tells you, hey, this is how far away this thing is.
Right.
So.
And so, again, to reference what we're talking about, both Celestia and Stellarium are two pieces of open source software that work on Windows and Linux and Mac OS. And so it allows you, there are actually two of them. With Stellarium, it is a planetarium software. So you actually can plant yourself somewhere on the planet and see what you would see up into the sky. And you can do amazing things like remove the atmosphere, which astronomers would love to do if they didn't die in the process. And you can see the constellation boundaries, because constellations are not just those anthropomorphic beings that we've connected the dots, are actually general areas in the night sky. So you can start learning the night sky based on the areas that are there, and do a lot of really cool things. And you can plan out when the next eclipse is going to be, and have an animation of it happening in real time. You can go back in time, forward in time. It's really fun. It's free. And since it's open source, any programmers out there that want to add to it, you're more than welcome to do that. So that is Stellarium. I'll put the link into the event page. But it's a great piece of software. I use it quite a lot in the virtual star parties, but since I'm hosting and producing, I'm not an octopus and can't do all the things.
Not all the things.
Not all the things.
So Mercury's current distance is 4/3 of the distance of the Earth to the Sun. So it is currently farther away from us than the Sun is. So I mean, if you can imagine, so let's say, so this is the Earth, right? Here's the Sun. Mercury is over here.
Right.
And it's actually off to one side because it's right now a morning object, so you'd be able to see it before sunrise if you're looking in the right place. Or if you have a setup like Paul does and you know where to look during the daytime, you can see it that way too.
Right. Now, we have a comment here actually stating that same thing, but in a different fashion. I'd like to go into that a little bit too. It's Ron Filipowicz. I hope I pronounced that right, Ron. But he says Mercury is around 1.335 AU. Mm-hmm. And so we use AU a lot, especially when we're talking about solar system bodies and things like that. But what are we talking about with the AU? What does it mean, and what is that? What's that distance?
Well, AU, I mean, I was in Philly for, grew up kind of near there. Yeah, so you try to get somebody across the street, AU. So,
right.
But for us, AU is astronomical unit, and it used to be defined as the average distance of the Earth to the Sun, but recently they redefined it and just said it's specifically this number of meters, and it's roughly, it's like 1.496 times 10 to the 11th. So let's see if we're going to do that. It's about 150 million kilometers.
Actually, can you do that in inches, please? How many inches is that?
No. I don't.
No, I'm able. I have my students do that to get used to the dimensional analysis. I have them do huge distances in inches.
And in inches.
Mean.
Right. So not furlongs. I guess if they're spending time at the track, then they have to know how long a furlong is. So.
Right. So yeah, when we're talking about astronomical units, we have it's been like the general average of distance between the Earth and the Sun, and so at 1.33 AU is going to be 4/3. So we're just talking about how far we are to the Sun plus 1/3 of that extra, and that's how far away Mercury is right now.
Yep. So got some questions out here. I got from Purnell Woodson, it looks like, asking what kind of telescope that Paul is using. I believe that's a Schmidt Casas, right, Paul?
Yes.
So so it's one of these deals where the light comes in the front. There's a piece of glass that acts to kind of correct the light a little bit. There's a spherical mirror in the back, so the light hits this mirror and then starts coming to a focus, and there's another mirror up at the front. And there's a hole in that mirror in the back, and so when the light hits the front mirror here, it comes back through that hole, and that's where you get your image from. So let's see.
And well, what's the reason why you would want a Schmidt Casas as to a Newtonian? That, the typical telescope where you're looking in the side of it, not the pirate one. That's a refractor.
Yeah.
But you can go and see Newtonians, and so you have your primary mirror come up, and you have your eyepiece on the side. Whereas a Schmidt Casas has it on the back end. Is there a reason that we would want to use that?
So Newtonians are by far the cheapest to construct. So if you're looking to get into astronomy and you don't want to put a big monetary outlay, but you want to be able to see some stuff. You want to be able to see some good detail on the planets or the moon, or possibly, if you don't live someplace with dark skies, something that you could pack up in your car and drive out to somewhere where it's nice and dark. Newtonian's definitely the way to get your feet wet. Just as an example, when I was a kid, I mean, my parents were very supportive about this, but they weren't about to go shell out a couple thousands of dollars to get me a Schmidt Casas as a kid. That just doesn't make sense. You don't know if it's going to sit in the corner, and they don't know how to use it. So, so they got me a Dobsonian, which is a type of Newtonian. Everybody who lived around me, when they see me get it out, it's like, oh, he has the Canon out again. So, because these Newtonian telescopes, the Dobsonian models, they look like a cannon, right? It looks like a mortar fire, something that fires a mortar. So they tend to be less expensive. They give you really nice views of just about everything. The thing is, though, they can be a little tricky to guide. We can ask, I guess, Corey Schmitz had built his own guidance system for one, and you should check out his.
Corey's a boss like that.
Yeah, that is not an easy feat to accomplish. But generally they're very, very good introductory scope, and they can give you a lot of aperture, a lot of light gathering ability for a lower price. Now, Schmidt Casas is going to be more compact, so it's easier to say pack up and take somewhere. But the thing is, you have to get the optics much more precise. There's many more elements involved. It's not just big mirror at the bottom, smaller mirror at the top, and put an eyepiece somewhere. It's all this bouncing of the light in between, so things have to be aligned a lot more. They tend to be more rigid in construction. But they're easier to put on a kind of mount that will track the sky, like the one that Paul's using now, or that I use for astrophotography. And so if you want to get in on that level where you want to start taking your own pictures, then you'd need something that can track the sky, and typically those are going to be more of a Schmidt Casas scope. Now, they do make Newtonians that have equatorial mounts and all, but generally the kind of preferred imager for deep sky work is going to be one of these Schmidt Casas. So
just a little bit more stable, and you get a better focal length without actually having the real estate too.
Yeah, I mean, this is the one thing I get a lot of flexibility with mine. I can take out, so I said, like, there's a glass plate here, there's the mirror on the back. That secondary mirror, I can take that out and put a lens there instead. And so now I have just the length of the tube as the focal length for the scope, which lets me get really, really wide shots, which is terrific for nebulae and galaxies. Or leave that mirror in and use a camera or an eyepiece at the back, and now I can do really good close-ups. So you get more flexibility, I think, with say a Schmidt Casas than you do with a Newtonian. But then again, I have the problem if I'm anywhere where there's moisture, that front plate, just gets covered. It's like the dew monster comes up and licks it, and that's it. There's my night's observing is done.
Right.
Whereas a Newtonian, you never have that problem because the mirror is so deep at the end of this tube here that dew doesn't become an issue. So.
Right. So we've moved along from planetary to stellar.
Okay.
And we've changed a little bit of what we're looking at. Paul, can you tell us what we've done here to change from going from Venus and Mercury to now looking at the sun, and why we see the sun a little bit differently than we typically would with just a regular filter?
Yeah, we're now using a hydrogen alpha scope, which is the little one on top. And a different camera. We're back to the DMK41, the monochrome camera.
Okay. So when we talk about hydrogen alpha, I mean, we're talking about a very specific, band of wavelength of light. Can you go in a little bit of detail with that about what we're talking about when we're looking at hydrogen alpha, and what does that mean when we get images like what we're seeing now?
All right, so you have to go back to a little bit of how an atom is put together here, right? So you have protons, which are positive, and electrons, and really, really tiny compared to the proton, which are negative, and so opposite charges attract. And so to build an atom, for hydrogen, for example, you take a proton and you stick one electron on it. Now, because of quantum mechanics, this electron can only live happily at very certain energies with respect to the proton. So they don't just slam right in, but it can happily live at what's called the ground state, which is the lowest energy level, essentially when it can be closest to the proton and have a stable orbit nearby. Or you can add some energy to the atom and the electron can move slightly farther away. However, it's positive proton, negative electron. They want to get as close together as they can again. And so in doing so, the electron has to give up some energy. And the way that it does this is it emits light. And so for hydrogen, if it goes from what's called the first excited state, so this is when it has the yay!
Yeah, that's my first excited state.
Okay,
it goes down from there.
And then it goes down back to the ground state. It has to give up some energy, and it does so by giving off some ultraviolet light. So this is higher energy light than our eyes can detect. The other thing that can happen, though, if it goes from the second excited state, which is the bigger woo, even more energy, right?
Right, yeah.
From there, falling down to the first excited state, not all the way to the ground state. If it goes to the ground state, you get ultraviolet, can't see it. Right? But if it goes from the second excited state to the first excited state, it gives off red light. And so when we're looking at hydrogen, what this hydrogen alpha is, it says, hey, I'm going to focus in on only this one particular color of light that comes from the electron doing this transition in hydrogen. And so one thing it lets us be a little more sensitive to is some of these features in the solar atmosphere that, typically if you look at the sun with a white light image, so you let in all of the light you can see sunspots. You can possibly, if you have a high enough resolution, you can see where the sun's kind of boiling up and then the hot gas kind of sinking back down, these regions called granules.
Right.
And that's about it. But if you look with hydrogen, then you can even see some of the light from hydrogen gas that's in these loops off of the edge of the sun that are called prominences. Let's see, and you get a lot more detail, and you can see features that aren't visible if you take in all the colors of the spectrum. It really just shows, in particular, how this gas is kind of moving around the edge of the sun and getting caught in the sun's magnetic field, and so it forms these loops above the surface as these charged particles, protons for the most part, hydrogen, are moving along that field. You can see these loops, these prominences, and so these are the kind of things that show up well with hydrogen alpha in a picture of the sun. So.
And I'm wishing I was on my laptop right now, because I've done a little bit of sun imaging myself, just using my binoculars and a white light filter and my webcam. And that's what we're talking about. When we're talking about white light, it's everything that's coming down to us. We're not filtering out one specific part of the spectrum. We're getting all of it and just taking out 99.97%, I think, of all that's coming through. And so we're seeing everything we would typically see just much, much dimmer. We're taking a lot of that energy out of it.
Right.
Because you don't want to look at the sun anyway, but then when you're looking at it through a lens and you're increasing that resolution, it causes bad times and melting and of the eyeballs and of your optics.
Yeah, this is the thing. I mean, there are probably some people out there who are watching who have tried setting fire to various objects or insects, whatever, with a magnifying glass. The idea there is you have a lens, and as the sunlight hits the lens, you get an image of the sun at the focal point of the lens. The front of your eye is a lens. If you look at the sun, you are doing the same thing, making a tiny image of the sun on your retina. Mm-hmm. You are burning a hole in your retina if you are looking at the sun for too long, right? Or really at all. I mean, don't look at it at all.
Right.
Yeah, you're essentially, instead of having it be the piece of paper or whatever critter you're doing bad things to, it's the back of your eye, and
right.
And you can't smell the smoke back there, right? Because but it's burning.
Yeah, you can feel it though.
Oh yeah,
you will feel it.
Yeah.
Now,
sorry, go ahead.
Yeah, we're and just so everyone knows, Paul's doing a great job. He's having a little bit of tech issues, but he's been able to bring it back online, and so the detail we're able to see now in his image is very different than what I would with a regular just white light filter, as far as getting the giant swath. So he has that very particular band of light coming through, and so he can see features of the sun that we don't typically get to see.
Right. In particular, I'm really loving this one filament is what it's called on the very right edge of the picture. So if you're looking on the right side, so here's the disk, and then over on am I mirrored for other people?
No, you're mirrored for me and everyone. Oh no,
okay.
You're mirrored for yourself.
Okay, so on the right edge of the picture, you can see this kind of dark line. It even extends out past the limb, out past the edge of the sun a little bit. This is one of these regions of hot gas that gets trapped by the sun's magnetic field. So we get the dual nature of how these things appear to us with just this one particular feature in Paul's shot here. You can see a region toward the top of the sun where you see these kind of little stringy things. That's a filament. If you see them at the edge of the sun, it's a prominence. And right now, with the shot he's giving us, you can see how a filament, when it gets to the edge of the sun, looks like a prominence. So this is a terrific example that we've got here of one, just how three-dimensional our star is. It's not just a disk in the sky; it is a ball.
Oh,
and
there you go,
so.
Paul.
Oh yeah. Okay, so there we go. And we changed the exposure a little bit to really show these prominences at the edge. And so now you can see that one, if you're looking at it as a clock face, it's like between 2 and 3 o'clock. And it's just kind of sticking off, looks kind of like a finger pointing up toward the top of the picture there. And this is one of these loops of hot gas, with the shorter exposure, you can see how it stretches across the face of the sun, and then now with this exposure, you can even see it extending past the edge of the sun into space. And you can see this in a couple of other places around the limb or the edge of the sun also when we change the exposure like this. So yeah, very nicely done.
Yes, beautiful. And we have another astronomer from the Southern Hemisphere with us today. How are you doing, Peter?
So I think you might be muted, Peter.
I think you're muted, yep. Or you just lost your voice, and you're doing a great job losing your voice. Yep, you're still having audio.
You're still muted, yeah. So.
And I saw a question, so if we can get your audio back on, someone actually asked a question about our broadcast a couple weeks ago about the observation of the transiting exoplanet, which sounds like a bunch of jargon, but what that means is we're observing right now with Paul. We're using some optics, we're looking at it, and then we have an exoplanet. So exo means outside of, and so there's a star that we were looking at, Qatar 1, and it's 550 light years away. So we have the speed of light, which is 3 times 10 to the 8 meters per second. That's how fast it goes, and it's really super, super fast.
For
Yet
our American audience, that's about 670 million miles an hour.
Right. Yes.
So, yeah.
So it's really fast, yet how far away this is, even at that speed, it takes 550 years for light to go from us to that star. So it's a really big distance. And what we are able to do, just based on where it's situated, this planet, this exoplanet that's not within our system, but in this other stellar system, we were able to actually watch the planet go across the sun, or excuse me, not the sun, that star, its sun.
Its sun.
Its sun. And so we were able to actually have the first ever live broadcast of that here with Peter Lake. And I was having a question here, and I hope Peter's audio is working here as I'm trying to pull it up. And we have so many comments because everyone's awesome. Here we go. It's Nick Rose. It says, with the recent live event dealing with the Qatar 1B transit, I was wondering if small telescopes can get data on exoplanet transits. Would my 6-inch f5, which we're just talking about the specs of a telescope, with the CCD, be able to get data of transits? I don't know if Peter's got his audio back yet. Because Peter was using a 1/2-meter telescope. So we're talking about a big mirror, and he left me a chat, so let's see here. Yes, but go for a very deep one. Okay.
So part of the thing is the dynamic range, like how there's a big difference between the way our eyes perceive light and the way that cameras perceive light. Our eyes can make adjustments for enormous changes in brightness. So you can be out on a bright sunny day, you go inside someplace that's really dark and has no windows. Yeah, okay, you're not going to be able to see for a couple of seconds or a minute or so, but your eyes will adjust and let you adjust to this extremely low light level. So our eyes see things kind of as multiples, that something is, maybe 10 times brighter than something else, or 1,000 times brighter than something else. And the systems that our retinas use to make adjustments can handle these kind of changes. For cameras, they do it where they say, well, I get this many more particles of light. And so the problem is that they'll max out somewhere. If you have what's an 8-bit camera, an 8-bit CCD camera, it's 256 intensity levels. So if it takes, say, 10 particles of light to trigger one intensity level, then it's about, a little over 2,500 to max out that one element on your camera. If you have a 16-bit camera, then if 10 particles of light get one element of your camera to register, you can go up to more than 650,000 particles of light and still be able to handle that range. So when you're talking about an exoplanet, you're talking about a dimming of the star by about 1 part in 100,000, 1 part in a million. So you
pretty
really
difficult to detect.
Yeah. So you really need you need some kind of 16-bit imager to pick up that small of a change. I mean, Peter would have more direct info on actually putting this into practice, but going off of what I know about how cameras are work, this would be I'd want something that has more bits so you have a greater range of potential brightnesses that you can detect.
Right. And what I'll do is I will put the event page, or excuse me, the link to our event that we had that for, which so you guys can watch the video of it, but also see the results of the photometry that we did. So we're just measuring that light coming through, and it was brilliant. So not only were we able to watch and see this happen, but you could actually see the dip in light as that happened. So you can see that there's less light hitting your detector for a period of time and then going right back up again. So it does a little dip down, and that's showing that the planet moved across the sun, its sun, that star, and it's blocking a little bit more light than would typically come to you. And then once it moved out of its way, it slowly creeped back up. and since Qatar 1b has a period of in orbit, I think of like 33 hours. It's really, really, it whips around that star really quickly. And so it transited in an hour and a half, I want to say. So transit means it just goes from the one edge all the way across to the other edge. And so it was able to do that within an hour and a half. So we got to see the entire thing happen within the length of a hangout. Are you back, Peter? Did you get your audio working? Nope.
Yeah, still no audio.
No. Oh, that looks beautiful, Paul.
Oh, wow. So the brighter regions that we're seeing here are associated with what are called active regions. So to the naked eye, using visible light, there'd be a sunspot there. I mean, we can even see the sunspot in this shot here. But there's a lot more going on. Whenever there's a sunspot, there are these very energetically entangled magnetic fields, and so this really jacks up the energy of the proton nearby. There are the protons and atoms nearby, so you get this region that's glowing brightly also near the sunspot. And so the term for this in the active region is a plage, so the French word for beach, because it looks slightly brighter like a beach would on the coastline of a...
I wouldn't go surfing there, though.
No, I mean...
I get sunburnt anyways, but I would literally get sunburnt.
Yeah, but, unless surfing as a vapor on a vapor surfboard, yes. Right? That could do.
Yeah.
But
not
yeah.
vapid, which I can be sometimes. It's vapor, right?
Exactly. So, I don't know, Scott. I don't know you to be vapid. I mean, but okay. If self-denigration is what we're into here, okay. Right. Let's see. So, but these brighter regions, they're accompanied with what's called an active region. So, an active region is a region where there is more intense magnetic activity coming out through the surface of the sun. So you can get prominences, you can get filaments, you can get sunspots, you can get plages, all of these associated with an active region on the sun. Now, speaking of waves, there are waves on the sun. Right? The sun is constantly producing sound waves that go through the sun. Now you're saying, like, wait, the sun's in space. How can you have sound in space? You can have sound if there's a lot of matter. And the sun, well, it's like 99.8% of the matter in the solar system. That's right. Plenty of matter. And so there are continual sound waves going through it. And so we can use this to track the motion of material under the surface of the sun. We can detect how these waves appear on the surface of the sun, and from that put together a picture of what's going on under the surface of the sun. It's a study called helioseismology. So here on Earth you have just seismology, and if you live in California like Scott or I, or New Zealand like Paul, then you know about earthquakes, right? So you have these waves, these pressure waves that propagate through the Earth. Well, the sun, even though it's not solid, it can have these waves transfer through it. And just like we can use earthquake waves to determine what's going on inside the Earth as far as its structure goes, we can use the waves on the sun to determine what's going on the interior of the sun. So surfing amazing. On the sun is not entirely, well, I mean, from some point of view, it is infeasible. Yeah, I guess from some point of view, it is infeasible.
I mean, unless you're like the Silver Surfer, you might be able to if you're the Silver Surfer.
But then you can anywhere. I mean,
right.
So that's a little bit different.
Oh, that's awesome. Now, I did see a question a little while ago, and it's not related to the sun, but I did want to address it. Let me see if I can find it here. I believe it's James McGee. Let's see here. And all right, so recently we have seen footage of an asteroid hitting Jupiter. But what happens once the asteroid enters Jupiter's atmosphere? What type of negative effects does this have on Jupiter compared to an asteroid hitting Earth? So negative is definitely relative. There are no, that we know of, life in Jupiter, and if it is, it's completely different than anything we know. But a lot of it has to do with what Jupiter's made of, and Jupiter's amazing. I can't stress it. Just the way that Jupiter's its role in our solar system is fantastic.
Yeah.
With not only how pretty it is in the great red spot and everything like that, and all the moons, but the way that it doesn't allow a planet to occur between Mars and itself, just because it's got its mass in the way, and it's breaking things up there with it's called orbital resonance, which is awesome in and of itself. But what do you think that would be, would it cause any long-term effects on Jupiter?
No, I mean the thing is, I mean, there's obviously what happened when Comet Shoemaker-Levy 9 broke up and each piece was slamming into Jupiter kind of one after another. But those impact scars were gone within weeks. Jupiter's atmosphere is so dynamic that it essentially would just stir that right back into the mix and be gone. So the thing is, though, because Jupiter's gravity is so much stronger than Earth's, that any object impacting Jupiter is going to hit it a lot harder than anything could hit the Earth. So on the way in, you can get an enormous release of energy. So you would first of all have the object slamming into Jupiter's atmosphere, compressing the gas beneath it. That gas would start to heat brilliantly and start to vaporize whatever is falling in toward Jupiter. So it's not like something falling toward the Earth where, let's say you had a large object coming toward the Earth, which didn't happen on the 21st. But, as something is going through Earth's atmosphere, it's burning up, but eventually you have a solid surface that it will hit. And we see effects of this. I mean, you can go to Barringer Meteor Crater in northeastern Arizona. You can look at geologic records of like the crater off the coast of the Yucatan Peninsula that you can ask a dinosaur about, or the one at the mouth of the Chesapeake Bay. So there is a bottoming out for meteorites hitting the Earth. There's not on Jupiter. An object can hit Jupiter's atmosphere and the gravity will just draw it in, draw it in, draw it in, draw it in. It's gas. At some point, the gas is dense enough that you can't tell the difference between a gas and a liquid anymore. Right. But this object would just get pulled in more and more. The heat would destroy most of it. As it fell in further, the pressure would go up, the temperature on the interior of Jupiter would go up, and it would eventually just destroy or disintegrate anything falling in toward Jupiter. So there's no solid surface for this thing to ever hit like there is here on Earth. It will leave some interesting markings in the atmosphere. But the thing is, again, it's all just gas, so it will get stirred up enough that give it a few weeks, you won't see a trace of that impact again anymore. So.
Oh wow, Paul, that is phenomenal what you're able to see. So you get an idea looking at through Paul's camera right now through his telescope, the three-dimensionality of the sun. So we are typically thinking of everything we look up as being circles or dots. We don't really get a chance to really think about things spherically just by looking up with our naked eye, but we can actually see how things are protruding out, and it is a sphere. And being able to think about it in a sphere, just in the geometry alone, I think for me was a huge step that really got me interested in astronomy. Was it's not just a bunch of dots and circles in the sky, but there's form there, and they're dynamic and they're changing, and you can see that there's something very, very powerful happening here. And then the magnetism in and of itself is causing that to arc around. It's just brilliant. It's absolutely beautiful.
So yeah, I mean that's one thing that's great again with the hydrogen alpha is this ability to kind of go to the shorter exposure and see more of the disk of the sun, or go to these longer exposures and see how something is looping off of the limb here like this. Now one thing, I did get some shots of Jupiter this past Friday night, so this isn't a live image, but yeah, is it okay if I share one of the shots?
As long as it's not green, because I don't want to make Fraser too angry when he comes back next week.
So, how about this one?
Oh wow! I suppose that'll do.
Okay. Yeah. So this is so again, this is Io. Right, so this is the closest of the 4 Galilean moons to Jupiter here.
So is that the Jupiter input-output system? Is that what
yeah, I'm pretty sure it's analog, and it relies heavily on sulfur.
Nice.
So, but you can also see, the North Equatorial Belt, the South Equatorial Belt. You can see what's called a festoon. So this kind of darker feature here that's kind of trailing off in Jupiter's atmosphere. So Jupiter's rotating about once every slightly under 10 hours at the equator. But the winds blowing, even relative to that, can blow from 200 to 600 miles an hour. So what you get are regions of low pressure where it's brighter. Low pressure allows clouds to go up higher in Jupiter's atmosphere where it's colder, and then they freeze as an ice, and the ice is very reflective.
Mm-hmm.
You get regions that are darker, and the darker regions are high pressure, so they allow you to see deep into Jupiter's atmosphere where it's warmer. Where it's warmer, it can cook up more complex molecules. And so more complex molecules tend to have less reflectivity. Again, living here in the Los Angeles area, we see these kind of cooked, more complex molecules hanging in the atmosphere fairly frequently, especially back up by the mountains.
Mm-hmm.
So,
and then we get to see, purple sunsets all the time.
Yep. So this was Jupiter from about midnight Pacific time on Friday night.
Oh, very good.
So, yeah.
It's live enough. I'm live enough.
Pretty darn live.
Technically, Paul's tomorrow, so...
Yeah. I got a wider shot, too. Let me see if I can grab that. Because this was, being a slightly wider shot, was able to pick up some of the moons of Jupiter here as well. I gotta see. I think I have a JPEG here. Because I think with Gary's screen sharing software, it only works with a JPEG, right? So
okay. You can also do the custom overlay on lower thirds if you want to.
Custom overlay on lower third. Oh yeah. Choose file. It's a small picture, so this might work well too. How about this? And turn that on.
Well,
okay. Well, there we go. Help! I'm being blocked. All right. So again, on this one, well, I guess you can't see my cursor now, but
I can see it.
Yeah, just to the left of Jupiter from your view, that's Io.
Right.
So, and it's about to transit Jupiter, so about to move over the face of Jupiter. Toward the top in that picture, the next object over to the right is Callisto. So this is the outermost of Jupiter's 4 Galilean moons, and then far over to the right is Europa. So this is the one that definitely has a lot of water, in fact, potentially more water than even Earth does.
Right, which is insane.
So,
if you think about that, looking at the ratio on it, it has more water on its surface than we do.
So, well, not on its surface. Right? We should be careful about this. On Earth's surface.
On Earth's surface.
But underneath a layer of ice that's somewhere between 5 and 15 miles thick. If you look at the density of the moon, if you look at how the temperature and pressure must change as you head deeper into the moon, that region of the moon has to have water, and if you look at the volume of the moon that it takes up compared with the volume of water on Earth's surface, there has to be more water on Europa than on all of the Earth. So.
Well, Peter, you jumped in, and I'm about to shut it down. We've reached our hour, but maybe if you could share a recent image with us before we go offline, and that can be our signing off image. That'd be beautiful.
While I was away, I was taking an image of M42 and Andromeda Galaxy.
Oh,
so
yeah.
I don't know if you've covered those yet, but
great way to go. So Peter's in Australia, but he's also running an observatory remotely in New Mexico. So he's able to get nighttime skies. So we'll be able to have both daytime and nighttime, and finishing out with another galaxy, I think, is a great way to end our show today.
Just give me a sec. I'll be right there.
All right. And I have to say, Paul, thank you very, very much for being the man. You just came through and gave us everything we needed, showed us 2 planets and a star, and an amazing detail. You were awesome, sir.
My pleasure.
questions.
Question here, I guess, from Bob Bradshaw about he's got a 4-inch mead and only sees a bright ball on Jupiter. So I guess the one question is kind of how big of a bright ball. If you're using low power, I mean, you'd see Jupiter as a ball, and you should be able to see the 4 Galilean moons. The amount of detail here, I mean, this is a 9.25 inch scope that I'm using, so it's going to be able to pick up some more detail. But the thing is, one thing, you've got to wait for the atmosphere to be pretty steady. The seeing has to be good, and then try cranking up the magnification. If you have a Barlow or so that you can put in front of the eyepiece, then that can increase the magnification of the eyepiece. It also dims the light a little bit. You're taking the same amount of light and spreading it out over a bigger area, so you have a better chance of seeing some detail. Don't be discouraged, though. I mean, I know that I kept track of my observations when I first got my telescope. It took me the better part of a year before I could even see the great red spot on Jupiter. So, I mean, you'll pick up the 2 equatorial bands first. If you can look a little bit longer, you'll probably see that the 1 equatorial band is now split, so that you can see, okay, there's 1 broad band on one side and then 2 slightly thinner bands the other side. The more you look, the more practice you get, the more you'll be able to see. The better trained your eyes will be at picking up this detail and knowing how to make adjustments to the telescope and all to be able to see it better.
Wonderful. Yeah, there's a lot that goes into the different types of telescopes and what you're trying to do. If you're trying to image, if you're just looking to have some fun. But yeah, I wanted to end here. Yes, M42 is something that many people have been waiting for, and I get to be a jerk and not let Fraser introduce it for the first time this season. So sorry about you, Fraser. M42. Thad, can you let us know what that is before we sign off?
So this is the Great Nebula in Orion. So again, if you have the 3 stars in a row is Orion's belt. If you come down from Alnilam, which is the center star in the belt, you'll see a grouping of another 3 stars that are fairly tight together. Around the middle one there is this incredibly large region of complex hydrogen gas and dust. Baby stars, it's a stellar nursery, just like we were talking about at the beginning of the broadcast. And so one of those stars is about the most massive star that you're going to see in the sky. It's an O-class star. It's estimated to have about 50 times the mass of the Sun. And so that provides so much ultraviolet light that it gets all the hydrogen around here glowing. Those electrons move up to excited levels and even ionize completely out of the hydrogen. So really exciting.
Wow! Yeah, that's right.
So, and then they separate, but of course, positive charge, negative charge. The electron is going to be drawn back in, and as it loses energy, as it comes back into the atom, you see this glow. And so most of this glow, if it was in color, would appear reddish. Mm-hmm. And that red, again, is showing where the hydrogen is. Now, you also get these dark lanes. So there's regions that are cool, that aren't being pumped quite so full of energy. These are good regions for forming stars. Right? Any place where you have a dark nebula like this, the gas is fairly cool, and all you need is a star kind of blowing up nearby as a supernova. Well, that's definitely going to happen in here. You have these massive stars that will end their lives as supernovae, and when they go, they can kind of set off a collapse of the nearby darker gas and dust, and as that starts to collapse, you get the nucleus of a new star. So stellar nursery, yes. Stellar morgue, also, yes. But with that also becomes the next round of star formation. So as stars are dying.
It's a circle of life, man.
There we go.
It's a circle of life.
I'm not going to do Elton John.
No, you totally should do some Elton John. Sing us out that.
At AAS, maybe.
Sing us. Okay, all right.
Yeah, you can see it's a bit close to the moon there too.
Yeah.
Oh yeah,
so
yeah.
Because you can see the moon sort of highlighting the edge of the filter there. So it's got a hydrogen alpha image at 300 seconds, but you can see a fair bit of detail in there. But tonight's not ideal because the moon's very close to that target. Well,
Peter, thank you for jumping in and seeing us out, and big thanks to Paul. I have to say, our Southern Hemisphere astronomers have really given everyone a run for their money. So let's step it up a little bit, guys. But I think it's also a good way to show that starting in the beginning of 2013, probably in February, I'm going to be setting up and getting everything organized for another virtual star parties featuring our astronomers on the other side of the country, or other side of the country, the other side of the globe, because you guys have a brilliant night sky that most people have never seen in their entire lives, and being able to show that I think would be fantastic.
Yeah.
So I want to thank everyone. Paul again from New Zealand, who's been showing us the Sun, Mercury, and Venus. Peter is in Australia, but showed us the Orion Nebula from New Mexico. Thad, thank you for being amazing as always.
Thank you, Scott, for hosting.
Yes, and I'm Scott Lewis. Thank you everyone for your questions, your comments. We should be back next week for an end of the year virtual star party. I haven't figured out how that's going to happen as far as we're doing anything special or if we're not doing it at all, but if so, we'll make sure to let everybody know. I'm here with Cosmic Quest. I'm the Education Public Outreach. I'm the Bald Astronomer on Twitter. Thad is Astro Thad.
On Twitter.
Paul is Astro Stew. And I don't know if I have Peter on Twitter.